Yeah, welcome everybody. I think I see also some new faces, so nice that you found your way, although it's raining cats and dogs, to ZUCMAP. Today I have to start my timer because I prepared probably too much, but don't worry, we're going to have lunch at 1. So today I'm going to talk about Hausdorff dimensions, but before actually starting my talk, I want to motivate it a bit, and I want you to start thinking, because it's going to be the main protagonist today, about the Cantor set. So maybe the big question about this talk, or in this talk, is actually, the notion of dimension for linear algebra in terms of, for example, vector spaces. There are also other notions, for example, in topology. And now suppose we have a kind of a fractal set, and what does that mean here? So for example, take the Cantor set, and for example, the right side, you do one iteration, and then you can check the right third. And then when you zoom into this right third, you kind of get a Cantor set again, and then you cut the middle third, and you can check the right third. And then you get the Cantor set again, and again, and again, and again. And the question is, can we kind of make sense of this in terms of dimension? And the answer is yes, and that is precisely the Hausdorff dimension. But let's do some recaps on your measure theory. So first let's just start in some metric space, and we are going to define this curly H alpha with delta basically as the infimum over the sum of those fk's. What are those fk's? So you're given a set in this metric space. You cover it with arbitrary sets called TFK, and you say, okay, I want that the diameter of those fk's are smaller than delta. And you can also define this for delta being infinity, and then it's just like you can just check every cover. And the infimum there is taken over the covers. So basically, this is not the Hausdorff measure yet, but a first observation would be, okay, what happens if we just make the delta smaller and smaller? So if we make the delta smaller and smaller, we are having less choices of covers. That means that, let's just call it here the alpha content, that this alpha content is going to increase. And what you may hopefully learned in your measure theory class is that when you take the limit to 0, this is then called what one calls basically the Hausdorff measure. And since it's increasing, this limit is equal to the supremum. You don't know yet actually if this is finite or not, so it could be infinity, and that is actually very, very important for later. And okay, so far I have not talked about what kind of measure you have, but basically in the measure theory course you would learn it's a Borel measure, so basically, yeah, you can calculate this for all Borel sets. All right, just some basic properties. So you have a usual sigma additivity property for the Hausdorff alpha measure. It is translation, and most importantly, especially the part scale invariant. So, for example, for the scaling, let's say you make the set E bigger with some parameter alpha, then maybe let's go one slide back. Since in the sum you scale the diameter also by this alpha, basically this is going to give you the scaling. Then if you want to pull it out, then lambda to the alpha, because you just can pull it out of the sum. And the third property is, okay, maybe you might ask yourself, okay, what would be some relationship towards the Lebesgue measure? And basically what you can show is that, take for example a Borel set in RD, then those agree up to a dimensional constant. So that is important, but I just want to I want to just say here clearly that the alpha here has to be really the same dimension as RD, otherwise this is not working. And this allows for funny computation, similar to, you take here kind of a circle in R3, a flat circle, and then you can, for example, calculate that for alpha equal to 1, you have this plus infinity. For H2, you actually have something that is similar to the Lebesgue measure. So you have some dimensional constant times pi, because this is basically the volume of the unit circle. And for H3, you again have kind of something flat, so you can show that it's 0. Okay, but so far I have not talked about dimensions, and this here is really the key lemma for this. So if you look again at what happened here, so here you have the jump from basically plus infinity to something finite to something zero. And the idea here is, okay, how's the Hausdorff measure going to change when you're changing your alpha parameter? And so let's check the first statement here. The first statement basically says, okay, if you have an S where your Hausdorff content is smaller than, your Hausdorff measure is smaller than infinity, then you know that strictly bigger t than s, this is going to be 0, and this is basically just follows by the definition. Because what can you do again? Basically, you can pull out the alpha t minus s, and then just apply basically the definition and take epsilon to be 0 to get the measure. But the real important point here is actually that this kind of allows to set up a dimension definition. So, okay, I have the following picture here. So basically, if you combine both points, and similar to what we have seen before, you know that taking, let's say, some set E in a metric space, but usually we work on RD, that your alpha Hausdorff measure is going to be plus infinity, plus infinity, plus infinity. And so your alpha grows and grows and grows, and then suddenly, bam, it makes a jump to 0, and then it stays 0. Yeah, and that is actually the notion of dimensionality here. And this is how one characterizes dimension. Maybe as a quick notion, do we actually care about the value of this specific alpha here? And the answer is, I mean, if you're really interested, yes, but usually not really. Like you're just really interested in finding that sweet spot alpha in the exponent of your Hausdorff measure where this jump actually occurs. And that is by no means an easy task, and we're going to see some examples for this, actually. So, and for people what are wondering about what's on the x-axis, it is actually this alpha exponent that you take if the influence, yeah?
I think the definition with the ZUCMAP is not really accepted because if it's 0, then it doesn't work.
I mean, I think, okay, we can discuss this afterwards. Because I think in RD, yes, maybe for arbitrary metric spaces, I'm not sure, but let's discuss this. But I think if you work in RD, you're right, but for general, let's see. Okay, and how are we doing? Okay, I have to check a little bit with time. Basically, one can then ask, okay, how does this dimensionality actually like let's say you have certain maps that map from sets to sets. For example, something that is Hölder continuous, how is this going to change the dimension of a set? And for example, here for Hölder continuity, you can show if you have a function that is on some set, Hölder continuous with gamma, you can estimate the dimension as follows, and this allows you to do some calculations. And this basically follows by, okay, you ask yourself, you have a cover on one set, and then you map this cover to another set, and then it either shrinks or increases, but you're always able to find this sweet spot for the parameter here by, for example, here calculating the Hölder or having the whole Hölder exponent at your hand. What I just want you here to see is just knowing the dimension one set can help to calculate dimensions of the other set. For example, here, if you take just something that is Lipschitz continuous, you see actually that the dimension is not going to change. Or actually, not directly going to change, but that here you're actually going to have equality. Yeah, so it's not going to change. All right. Okay, but let's actually speak about how to calculate this, because I don't think that is clear yet. So let's stick to a set E in RD. So the question is actually, how can we find the sweet spot between 0 and D here, such that for very small epsilon, so just to the left, maybe let me remind you of the picture again. And here you have your alpha of E. So here you had the plus infinity. Here was your dimension, h of your set E. And then here it continues to be 0. So really small before, this is going to be plus infinity. Epsilon afterwards is going to 0. How do we find this? Usually the plan is the following. It's not so easy to guess at first actually what this alpha could be. We're going to see this in a second. And so you kind of need some heuristic argument saying, hey, if I know this, I have some calculation, and this kind of calculation suggests that this alpha should be, for example, 1/2. Then having this guessed alpha, what you need to do in order for the definition, in order to apply the definition of dimensionality, is you need to find an upper bound for your alpha Hausdorff measure on E. And usually the way you find this is the easier part, is you somehow have to choose one smart cover for E, such that you find a uniform bound in the delta. And then just by taking the definition, the alpha Hausdorff measure on E is exactly the limit of the alpha Hausdorff content with delta. And if you have found this smart cover, just one, to bound this uniformly, you're good. We're going to see this in a second. And then the actually much more non-trivial question is, how can you provide a lower bound for all delta covers of E? Because the alpha content or the alpha Hausdorff measure is defined as the infimum over all the covers. So you need to find a lower bound for all the covers, and that is kind of hard because there are a lot, basically. So how do you establish a bound like this? So this is usually if you know me in playing cards, this is usually the for experience part, as I say it, which means it's a lot of fun but difficult, and maybe sometimes you do some mistakes, I guess, calculating it. So let's give an example. So the example I want to treat again is this Cantor set that we know. So what is it? So you have a subset. So basically you take 0, 1, and then in each iteration you divide the middle third. Then in the first step you divide the middle third. You go to the left side, you divide the middle third, and again, and the same on the right side again, and then you take the intersection of all those generations, and this is the Cantor set. I think most of you guys have encountered it in probably topology or analysis. And the question would be for this fractal, okay, what is actually the Hausdorff dimension of the set? Because so far, maybe the first idea would be, okay, we know that the alpha Hausdorff measure agrees with the Lebesgue measure for if we are on the same dimension, right? So here we are in dimension 1, but the problem is that the Cantor set actually is usually the first uncountable set that you meet that has 0 Lebesgue measure, so this kind of does not really help. And then the question is, okay, what can the dimension actually be? It has to be something smaller than 1, but we don't know yet. Okay, so you would start with kind of an heuristic argument, and the heuristic argument here is directly using basically the nature of the set is, okay, let's split into the left and the right part. Okay, you have this, then you can again scale by 1/3 to the power of alpha using the scaling property, putting both together. Then you have the inequality, equality regarding the alpha Hausdorff measure, and then you basically can solve for this alpha, which is then log 3 2, or ln 2 over ln 3. But this is yet only a heuristic. This is only, okay, if I have an alpha such that we are actually here in this sweet spot somewhere, then, okay, this alpha should be this here. This is not a proof yet. This is only blind heuristics. But you kind of need that thinking to have a good idea about what it would be. And for the upper bound, it's actually not so hard, because the nice thing about the Cantor set is then if you're in a generation, let's say CK, and you kind of take a cover only over this CK generation, then that is also going to cover already the whole Cantor set. So no matter which delta you take, you can always find K big enough, so you iterate the Cantor set long enough such that this 3 minus K is actually smaller than this delta. Then you just can take a cover which would be all the sets on the Kth or larger than this Kth generation. And then, okay, you just can plug it into your definition of your S delta content, basically. So you have 2 to the power of K sets times, okay, what is the diameter of the set? It is 3 to the minus K, and you weight by this alpha. But this alpha was log 3 over 2, and this gives you a 1. So here, for this alpha, you already know, okay, Now, if you take this delta equal to 0, you know that you are, for that, okay, sorry, that should be an alpha here. Yeah. So you know for your alpha Hausdorff measure that this is bounded for 1, and this is already the upper bound you want to have. So, which is very nice. So now for the lower bound, it is actually a little bit more complicated. So basically, having any cover, one tries to establish a bound of 1/2. And then using some measure theory trick, you basically say, okay, I don't want to calculate it for this, but you can find finitely many open sets, D1 and D2, that cover your cover. However, that they have a little bit less of content. And then you just can basically bound these open sets by using the nature of the Cantor sets and some tricks. I have it here, but I think because of time issues, I'm going to skip on this one. But I'm just wanting to give you one message here. First of all, it's a nice exercise, but not an easy one. And the problem here is already the Cantor set is kind of a deterministic fractal. It's one of the first ones you know about. And this is already kind of hard, or it takes time. So the question is there actually a better method to establish, especially those hard lower bounds? And the answer is yes. So let's see. Okay. And the idea kind of is that union bound arguments are very good. So let's go maybe back to the definition of your alpha content here. So here you kind of see your set is contained in some cover, right? Where this cover is set as a union of sets. So the idea would be somehow maybe you can find a measure that, I'm not going to say the property set, but if you somehow can relate a measure and the dimension, then you might have a strategy for having lower bounds. So maybe let's just go to the slide. So the idea here is, okay, you consider mass distributions. Those are just, you have a measure mu on Borel sets of your metric space such that it has finite measure. And then the idea is, okay, maybe you somehow can relate the alpha content and the union bound argument together. And so basically what you have is, you have this lemma which tells you, okay, if you somehow find a measure mu on that given set, such that for closed sets V that have diameter smaller than delta, and you have the following bound, so mu of the measure is smaller than c to the c times the diameter to the power of alpha, then you can bound your alpha content, your alpha Hausdorff measure of M or your set whatever by below. And that is very nice because this allows you basically to come now up with a uniform lower bound for your alpha Hausdorff measure. And the trick here is, it's a very smart idea. I tried to find who came up with it, but I don't know actually. I mean, it's an older trick, but it's very nice. So basically, the idea is, okay, take any cover of your set, for example, or your metric space here, that is small enough for some delta. Then, okay, if you take the closure of those sets, it's not going to change because the diameter of the closure is going to stay the same. And then basically you have those sweet conditions with respect to the bound, and that allows you to kind of do this chain of calculations, and at the end have something that is independent of this cover. Then you shuffle it around, you shuffle the C around, and here basically this is going to be your alpha Hausdorff measure. And then here you just say, okay, no matter which cover I took, I have this bound with the measure mu of M divided by C. And as a lower bound for every cover plugged into my alpha Hausdorff measure. Hence, no matter which cover I take, I can take the infimum, this still holds, and then just basically let data go to 0 to have my alpha Hausdorff measure. So the main takeaway here is just if you want to calculate lower bounds for Hausdorff dimensions, I mean, you can try the direct method or the definition, but actually it is much better to try to hunt for some mass distribution and try to apply it there. Okay. So let's see if we can do that for the for the Cantor set again. So the idea, what I think would be nice to try is, okay, what about, can we somehow rewrite the Cantor set into something that is a little bit, more, where we can somehow work to find a measure? And the idea is yes. So one, for example, can represent the Cantor set as this free-adic expansion. What does this mean? So intuitively, you just take the Cantor set and you have your sum over there. And for every point in this Cantor set, you can rewrite it as a way to going on the left side or the right side of this tree. So 0 for an equal to 0, this means you would go to the left, and for an equal to 2, you would go to the right. So you can represent every number in this kind of tree structure for the Cantor set. And how does this help you? So for example, let's try out some numbers. So for example, the number 1 would be just 2, 2, 2, 2, 2, 2, 2, 2, because you always go on the right side. And for example, 1/3 would be, okay, first I go to the left, then I go to the right, and I stick to the right, and I stick to the right, and I stick to the right, and so on and so on. This is very nice because now you kind of have a tree structure, but also when you speak about measures, you kind of could see now that when you try to find this mass distribution, you could kind of think of points in the Cantor set as taking basically countable many coin flips if you go to the left or you go to the right with here equal probability. So for example, let's say we go to 2, then it would be, okay, the chance that we go twice to the right would be 1/4 because we go twice to the right. And that is actually very nice because now we have a new representation of the Cantor set, and actually with some measure theory you can actually prove that there exists a measure on it that satisfies the bound, and that given, let's say, finitely many paths, or like let's cut down a path into finite, or if I give you any path, and I just ask you, okay, can you give me the chance that I do finite many steps, either the left or the right way, then this is exactly given by the chance of going to the left or going to the right for this path. All right, and so yes, then let's go back to the mass distribution. So the problem a little bit with the mass distribution here is that here you need to bound arbitrary closed sets, and that is a little bit awkward actually for the Cantor set because now we have this free adic expansion. So what you actually can do is, how much time do we have? Okay, 20 minutes. So what you can basically also show is that, okay, actually do I have to establish this bound for all closed sets, or are kind of only free adic intervals enough? And the answer is yes, because you kind of can do tricks in rewriting a given interval or an open ball in 0, 1 by free adic intervals or multiple free adic intervals, but then do calculations that show that your alpha Hausdorff measure actually is only going to change by a constant if you do this trick. So basically you can work with those grid measures and the dimension stays the same. So let's, for example, take this ball or this grid measure, bx 3 to the minus n, and we want to now estimate this. Okay, maybe the ball here is not big enough, so it's not the best way to write it, but think of an interval, of a free adic interval with kind of a radius 3 to the minus n. What does this really mean? This means that taking 2 points in it, going back to our graphic that we had before, is that, okay, since they're 3 to the minus n close to each other, the first n steps taking in this graph, they have to be the same. Yeah, because that is exactly the given distance in the free adic expansion. So for example, let's take those 2 numbers here, x1 and x2, in this free adic interval. Then, okay, you would both start with 0, take n steps, and then on the n plus 1 you can differ. All right? And basically by the construction and thinking about those IID coin flips, the question would be, okay, how many different choices then actually do you have for points in such interval? And since you only go left or right in one step, and basically here, so for this 3 to the minus of n, you then only have 2 to the power of n choices, because you can, the first n steps have to be, they have to be distinct choices, right? They have to be the same. So how many do you have here? It is exactly given by 1 over 2 to the power of n, which then, using this alpha, it is 3 to the minus n times alpha. And then applying the, basically applying the mass distribution principle, this would give you the corresponding this would give you the lower bound for your Hausdorff dimension. Okay. So this is one way to do it. Another way would be potential methods. So what are potential methods? Basically, you would define this S potential at a point x given in Rd, and where you again have some mass distribution, and then here you have this S energy given as the double integral over this mass distribution with respect to some people call it kernel, but basically here you can take x minus y to the power of s. And kind of the basic idea is, if this integral is finite, then mu is going to spread the mass kind of evenly around your fractal, so the dimension has to be large in some suitable sense. If there's some physics people, I think this S equal to 1 corresponds to something called Newton gravitational potential. So there might be some physics intuition behind this, why this works. If there's any physician here, then I would really love to maybe speak a little bit about the intuition about this, because also when you check the proof, it is not quite immediate that there's actually a link between Hausdorff dimension and this S energy. It is quite subtle. And I also don't know who came up first with this, but it just works, and it's very nice, and it's a method used a lot in practice. So basically here, if you want to have a bound for the lower dimension, then you just need to make sure that your S energy for your mass distribution is smaller than infinity. And the question is now, okay, which one is more useful? So now you have both methods, both the mass distribution principle and the energy method. And it might seem right now that, okay, maybe I should use one or the other, but which one is actually better? And actually this picture is telling only half the truth, because usually they're used in different kind of settings. So the energy method, as we are going to see right now, is usually very, very useful with respect to fractals that are given by some, or basically random fractals. Because here you have this integral, but also, let's say you average, or you take basically expectation of this integral and apply Fubini, you might, having a fractal at hand and this mass distribution, you might not know kind of deterministically how this measure behaves, but if you put your expected value inside, and it's something that is given random, you kind of have an idea what it does on average, basically. So, yes, let's... Okay, in the last 15 minutes, let's discuss this. So I thought I would have a pointer, but I don't, so let's go. So let's say we have some now random Cantor set. And the idea here is, okay, still in the E-kth or in the kth generation, you have 2 to the power of k sets, but the size that you take, you kind of want to just draw this randomly from some given distribution. So there are 2 distributions here, the green one and the yellow one. And what you basically say is, okay, still each interval here has 2 children, the left and the right one. And the ratio of the size from the left to the right one is given by, so for example, if we have interval E1, and so that means the first interval on the left, and we go to the second interval on the left, so I1.1, so the left children of the first interval, then the given ratio between those is going to be equal to this C11, where this basically this C11, you kind of take it the same as some given C1, which you draw out from the you draw randomly from the green probability distribution. And the same with the C2 one, where this distribution is kind of thinner and more concentrated. So here you would say, okay, for the C2, given on, if you take, for example, right steps, so if you go from I2 to I22, you want that the ratio of this is going to be always equal to C2, no matter how far you go down into the Cantor set. And this gives you some random construction. And also what is important here is that your A and B that you take, so the C's are bounded by this A and B's, and you want actually B that is strictly smaller than 1/2. Why do you want to do that? For example, in the ordinary case of the Cantor set, you basically, so if you would not do this, then your Cantor set kind of gets too fat, and then it's not going to have Lebesgue measure 0 anymore, so it's going to be maybe 1/2, something like this. And then you already know, okay, directly the Hausdorff dimension of this has to be 1, since you're in the one-dimensional case, and by the property that you kind of can relate the Hausdorff measure, the one Hausdorff measure to the one-dimensional Lebesgue measure. And what you also want is those ratios here. So the I1 to the IK, they are all independent except when you check your brother and sister, basically. Those are the only ones you don't want to have independent. And the question is now, can we guess the Hausdorff? Can we calculate the Hausdorff dimension for this set? And the answer is yes, amazingly. And there are also other constructions of random Cantor sets. So first, let's try to guess the dimension with some heuristic calculation. Is again, you take the alpha Hausdorff measure, then you just take some expectation, you do the same trick, you pull out the C1 and C2. What was the C1 and C2 again? The C1 and the C2 are always the same given length ratios going from going to your left children or to your left child and going to your right child. So then here, so you get the following equation. You basically solve for the expected value of C1 to the power of alpha plus C2 to the power of alpha, and this has to be equal to 1 due to this heuristic. And so you would guess, okay, maybe if I can calculate the Hausdorff dimension, then this alpha should be actually given such that in expectation, since now you have a random construction, right? This C1 and C2 is drawn randomly. In expectation, the Hausdorff dimension should be almost surely given by the alpha that's going to solve the following equation. And a quick sanity check. So you could ask yourself, okay, does this really align with the Hausdorff dimension that we had in the deterministic case? And the answer is yes. You just can take C1 and C2 as deterministic random variables, basically. And then if you solve here, you see you have basically the same dimension. Okay. So how can we actually do this? So just to introduce some notation, for an usually the interval on the kth level was denoted as I, and then subindex I1, I2, ... ik. But here I'm going to shorten the notation and just say, okay, the interval on the kth level, I'm just going to call it bit I. Write IL or I big L and I right L for the left and the right kid. Basically, we are going to write the conditional expectation as follows. For those who did not take probability theory yet, is basically think of this as an average over X given the information of Fk. What is the information in Fk? The information of Fk are all the sequences here yet that are basically smaller than a k. Than this k here, or on the kth generation. And the idea for the lower bound is again, okay, first you need to bound this alpha delta content. And so you take arbitrary delta. You always still can find a k that is kind of big enough than this bound, such that if you have then a cover, you have the following bound, you can plug this in. But now the problem is, since this is not deterministic anymore, and you don't have, let's maybe go back to the old case. So here you really had the nice cancellation with the 2 to the power of k and 3 to the minus k times alpha. This here is not apply, like this does not apply again, so you actually don't know if this is now finite or not. So you still kind of have to find now a bound given the right side. And how do you do this? And the idea here is actually very interesting, because you can start to use martingales. So for now, consider this family of random variables xk that are fk measurable. And what is this xk? This xk is now just nothing else as the sum over all the intervals on the kth generation times the power of s. And what we want to show, we don't know it's a martingale yet. So this would be the first step. And for those, again, who don't know martingales, just think of them, just think of the following equation where you say, okay, the average of your cave plus 1 generation given the information of your cave generation is exactly, again, the random variable given xk. Yeah, so averaging over the next generation, given the information of the generation before, is just exactly here the length of the cave generation. And okay, why does this hold true? So you could start with one interval, and yeah, you just go as follows, given the information of fk. Then, okay, what do you know about the length of those intervals? So the length of those intervals are always given by the ratios times the length of the interval in one generation before. But we said before in our construction that the ratio of the lengths is never going to change. It is always given by, for example, C1 if you go to the left or C2 if you go to the right. And yeah, basically you are going to plug this in and you have the following. Then, okay, you already know what is the average over one interval. Then you could ask yourself, okay, now I want to average over all the intervals in my cave plus 1 generation. You do the same calculation again. And basically, yeah, here you just sum up the right side with all of the cave generation intervals. And then you again take expectation. And since, okay, this has to be flipped here. Since we said that this S, or sometimes I also call it alpha apparently, since this S is set such that the expectation here should be 1, you actually get, okay, this now has to be 1, so you basically showed the martingale property, or that here, this length, basically you showed that your family of random variables is a martingale. Okay, why is this useful? Let's see. So basically, you can go even further, and it is an exercise given in Falconer's book that this is an L2 bounded martingale. So you have this uniformly narrow bound, and we know by some probability theory this converges in probability to the x as k goes to infinity, and you even know the expected value of this. The problem is it still could be that this x here, this xk converges to 0. But actually this is not possible because you kind of can set up the events. Okay, you know that the length goes to 0 if both the length on the right hand side and the length of the right of the left and the right hand side go to 0. But the left event has chance q, and by using the independence except 2 children, you can show that the right hand side has probability q squared. So yeah, this is actually not possible because then q has to be equal to q squared, and you're in a probability, so it has to be between 0 and 1. So here definitely has to be 0. But enough probability theory for you today. I know that not all of you took the course. Basically, what that allows is you can find random numbers m1 and m2, such that you finally have your upper bound, which is actually finite. All right. So let's go for the lower bounds estimates. And here I'm a little bit sus of Falconer's books. But basically what he says is that, okay, you can construct a mass distribution, this mu I, given as the following limit where you say, okay, the j's that you take, the j's that you take inside of this I, in the jth generation, you let it go to 0, and in the limit, this is going to give you a mass distribution that is between 0 and 1 almost surely, such that the following properties still hold. So if you average this mass distribution of the ith interval, given the kth generation, this is I to the power of s, and the right side is that you can dissect this ith interval into the left part and the right part of its children. And then he says, okay, this is actually enough, and he says, okay, there are some measure theoretic shenanigans going on such that you actually can prove that this mu extends to C with support given in this random Cantor set. So I want to take this kind of now as granted and use this to say, okay, can we actually, using the energy method, can we actually give a proof for the dimension, for the lower bound of the dimension of the Hausdorff, or for lower bound of the Hausdorff dimension? So let's go back. What do we have to do? Yeah, so basically what we have to do now is here bound our S energy given this mass distribution that Falconer constructs, and showing that almost surely this is going to be finite. Okay, so what do we do? Okay, so we have 5 minutes left. I'm probably not going to go over the whole calculation, but the idea is basically you go just step by step. So you would ask yourself what happens on the cave level. And here you have a nice estimate for, okay, for 2 given points, x and y, there's going to be one interval in some cave generation, and you have a good estimate on this here. So usually you always start with something like this, then you say, okay, this I cannot totally work with yet, but I know what we have on average. So you would just then take basically the average given given the information of the cave plus 1 generation. Then use the properties constructed from this mass distribution to then basically here get a final bound. So here then you already have a final bound basically for what happens on one interval. And then the idea is just go, okay, just let's iterate this. So if you know one interval, let's just sum over all those of all of the cave generational intervals. And this is something you can do very nicely due to the linearity of the integral. And then, okay, in the last step, okay, so now you know what happens on the cave level, basically, or you know the average of the sum on the whole cave level generation. Then you can do the Cantor set directly by just saying, okay, this is basically the same as, okay, if you just sum over all of the cave level generational intervals, and then for the 2 inner, basically for the first sum and the second, and the 2 integrals, you have everything from the first and the second step, because you build it up by just first knowing what you do on an interval, then on the cave generation, now you kind of provide a bound for the whole random Cantor set as a whole, and just applying the energy method then at the end is basically sufficient to say, okay, for this t here we can bound the dimension by the c, and then the question is, okay, what is kind of the critical t until we can do this procedure? And if you plug this in, it is actually going to be where is it? It is directly going to be the t such that this is going to be hold and this suffices. Okay. Maybe one last word. So we had this here before, right? So here, maybe as the main takeaway for the energy method, I just want to stress again out that the energy method here, why was it so good? Because basically you had the calculations here, and you don't fully understand what your mass distribution might do here, just plugging in an interval. But the nice thing is usually with those measures that you kind of construct is that you know what they do on average, and that is why it's kind of so useful and especially used in, for example, probability theory. And I mean, I hope that the main conclusion for today is that the direct method is not the best, but the mass distribution principle or the energy method is always worth a try if you have deterministic or random fractals. And yeah, I have more slides, but I think it's good to stop here. And thank you guys for listening, and let's have a lunch. Yeah. Yeah, first of all, questions. Was a lot in 45 minutes, I know. Yeah.
Just one question. So usually at the value of the dimension, we don't really know what the measure should be. Like it could be anything between 0 and infinity.
Yeah.
And I was wondering, because I think I've read or heard somewhere that when you look at the Hausdorff dimension for random objects,
Mm-hmm.
usually at the value of the dimension, this measure is 0. And I was wondering if you had any insight on that. Like for instance, the 0 set of the Brownian motion would be such an example.
Yeah, let me think about this. Because for the 0 set of Brownian motion, I don't know it directly. Because the method I know there would be to apply a mass distribution on the record times, right? On this, you kind of would using I think the idea was if you have the reflection principle, so the Brownian motion is going to hit 0 if the absolute value hits 0. But you can show that the absolute value of Brownian motion in distribution, I think, is the same as and now I'm not quite sure, as kind of record times minus the usual Brownian motion distribution. This is something I have to look up. I'm not 100% sure. And so, unfortunately, I don't know the proof for if you use, for example, the direct method. But for me, it kind of makes sense as well. Because if you think about those random fractals and the energy method is kind of really, you kind of really have this limiting behavior. So usually you always show that here you have 0, but then also same with this t here, you go closer and closer and closer, and you kind of then, as maybe since you take the supremum and the infimum here on average, it might be actually 0, but yeah, I don't know other examples, because, for example, in the AQG theory, one also uses the energy method, and so yeah, let's discuss at the apero. Yeah. Okay. Other questions? Or I think Ritvik is there. Okay. Yeah. Okay. Thanks, guys, and I hope you learned something, and see you soon.